Few minutes, we're going to talk about the difference between real and ideal. So far this year, most everything we've discussed has been in an ideal world. But in the real world, we have limitations on what we can do. And when I say that regarding electronics, I mean that all of our devices, being that they are real devices, have to find a way to do what it is we're asking them to do. So a voltage supply is an excellent example of that. We know that the voltage supplies we're using are not pure voltage supplies. We're using batteries. And as a battery goes, a battery's ability to produce current and maintain a potential difference is based on a chemical limitation within the battery. Now, we could try and find other voltage supplies that might have fewer limitations, but they're all going to be limited in that they cannot provide infinite amounts of charge. Now, the 6-volt batteries we use in class are good. They're solid. They have a large reservoir of acid available to them. They can produce and dump a lot of current. But probably one of the easiest things to demonstrate here is the nature of the real versus ideal. In the case of this, the resistance was getting smaller as we went this way. What's happening to the voltage?
Increasing.
Did you all notice that the voltage got smaller as you had smaller and smaller resistance? So, did the battery change? Now, did you notice that as you went from 3 bulbs to 2 bulbs to 1 bulb, the bulbs got brighter? Obvious, right? Because the resistance was going down, you were drawing more current. As you're drawing more current, the bulb was getting brighter. Obvious enough, right? But the voltage was decreasing. That should have been clear. And I bet that the battery produced about the same amount of voltage when there was no resistor on there and when you put the 10,000 ohm resistor on there. But I bet the bigger changes occur when you started to put that just 3 bulbs, then 2 bulbs, and 1 bulbs. You should have seen dramatic differences. And if not dramatic, clear differences. Now, when I say dramatic, older batteries would have produced a more dramatic difference because they're running out of acid. Newer batteries can probably provide a lot of current. So depending on whether you are quick enough to get one of the newer batteries or you got stuck with one of the older batteries, probably determined how well you were able to see this. But batteries have internal resistance. It's not an actual resistance. What it is a limitation on their capacity to deliver current. So it's not like there's a resistor inside the battery. That's not what it is. But the internal resistance is a limitation. And that limitation is expressed as an inability or an ineffectiveness to produce current. And how it manifests itself is in a loss of voltage. I want you to see how this works in practice, because we can't take the battery apart to figure out what the internal resistance is. We can, however, test the battery to get an idea for how much the internal resistance is. Now, before we have this conversation, there are a few things I do want to throw out there, since I want you to be good scientists, but I also want you to have an understanding of our limitations as students. First, resistance is affected by other things that I have not talked about. For example, resistance is temperature dependent. As resistors get hotter, their resistance changes, which is why the bulb's resistance differs the longer you have the bulbs connected, which is why I said over and over again, don't leave the bulbs connected very long. Not only will they get hot enough perhaps to burn you, but they change their resistance over time. Now, this is true for all resistors. But the batteries have an internal resistance, what we call it. But if you'll notice, the batteries also tend to warm up over time. And if you don't notice it there, you probably notice it with your cell phones, that they get warm under active use. It's the battery warming up. They can become critically hot, which is why most phones today have protection circuitry in them to ensure they get shut down should they get too hot. Have you ever been outside long enough with your phone for it to stop working before it gets ejected? Well, that's the protection circuitry, kicking in to ensure that it doesn't hurt itself. So here's what I want you to consider. We're going to do this very fast, and it will not take you very long. Inside the battery, at one time, was the perfect mixture of acid slurry and cathode and anode in such a way as to produce a perfect 6 volts. In the battery, when they did the calculation, they ensured that they had a perfect 6-volt cell. It's probably multiple 1.5-volt cells actually, but who's counting? But it was connected to, it's not an internal resistance, but it presents as an internal resistance. You'll see what I mean in just a minute. We're going to connect an external resistor. We're going to assume that our battery has a perfect internal 6-volt electrolytic connection, but that it's hampered by this internal resistance. And we're going to say that the internal resistance is very small, 0.5 ohm. Our meters can't measure the actual voltage of the battery. Our meters are actually measuring the voltage of the internal resistance. That's what they're measuring. So when you connect your terminals to the battery and you're measuring across the terminals of the battery, you're measuring the voltage drop across this resistor. That's what you're measuring. So here's what I'd like you to do. Let's assume that our external resistance starts at 100 ohms, then is 10 ohms, then is 5 ohms, 2 ohms, and 1 ohm. What I want to do is show what our measured or predicted voltage would be under all of these circumstances. For example, in our first circuit, we have a power supply, the internal resistance, and the external resistance. Taking the battery away, this is our circuit. 6 volts, 0.5 ohms, and our first resistance is 100 ohms. If I reduce the circuit, that's 6 volts connected to a single equivalent resistance of 100.5 ohms. What voltage do we measure across this bulb or this resistor? Do the calculation. Find out the current in the circuit. Take the current back one step, apply it equally to both resistors. And find out what the voltage is to our applied resistor. This should be super easy. 6 volts, 100.5 ohms. You done yet? It's not hard. Did everybody do the same thing? Did your 6 divided by 100.5? You found the current to be 0.0597. And you multiplied to get the voltage and found it was 5.97 ohms. Pretty good? Pretty straightforward? All right. So now that I've shown you what to do, I want you to measure the external voltage of the battery. This will be the voltage across the terminals for each of these cases. The thing to realize is that the internal resistance doesn't change. It's always 0.5 ohm. What will all of these externals be? Just repeat the problem. We did it for 100, now do it for 10. At your table, break it up. There's 4 left. Many tables have 4 people. Give somebody 10, somebody 5, somebody 2, and somebody 1. If you're stuck with only 2 people at your table or 3 people at your table, sorry.
I got one.
So this is always 0.5 and this is going to be the new value?
Yeah.
So there's an internal and external resistance.
6 minus the internal. That's how you can show the external.
Internal was Wait, what? Okay, what's your confusion?
I don't know if we can capture that.
You multiply.
Oh, you divide those 100.5 times the voltage.
So both are the same.
Yes, voltage for either one.
Wait, what's the other one?
I'm still with her.
Yeah.
Okay, gotta let him
But I think it would still work.
We about done yet?
You can.
one almost
What?
Like this, but
Yeah.
oh, that makes sense.
If you're having trouble, just come back over here. Because I'm hearing some distress. It's not a big deal. Let's say we're doing the 5 ohm bulb. Total resistance, 5 plus 0.5. The current's got to be 6 divided by 5.5. So I get 1 point something there.
1.0.
I get 1.09. Is that what you guys got for the current? So bring that back up here. Multiply it by the 5 ohms. I get 5.45 volts. All right, meals table. What'd you guys get for the 10 ohm bulb?
We got, the voltage was 5.71 volts across the external.
All right. Alex's table. What'd you guys get for the 2 or the 1 ohm?
4.8 volts for the 2 and the.
Okay, that's good. 4.8 volts for the 2. All right. Marco's table. What'd you guys get for the 1 ohm?
I got 4 volts.
4 volts. Now, this does not match your experience, but it does show the trend, doesn't it? Now, sometimes the internal resistance of a battery is relatively high. 1/2 ohm is a relatively high internal resistance. Clearly, a current limits your ability. Right? We see a clear deduction in the voltage as we reduce the resistance. The bulbs are about 2 ohms each. So when you added them up and started with 6 ohms, you're already starting with a relatively small voltage there. I'm sorry, relatively small resistance. And you drop down to about 2 ohms, and most of you probably still had over 5 volts. Anybody's battery drop below 5 volts? All right, which tells you that the internal resistance for those batteries is probably low, meaning they have a good ability to produce current. Now, if we had done this experiment with like a AA battery, do you think the results would be better or worse? Sure. A AA battery is going to have less access to the acid, therefore it's going to have less ability to dump charges. We start reducing that voltage supply, start reducing that resistance load, and we're probably gonna see the battery stop being able to produce the current that we're requesting. And we're requesting current from the voltage source. Now, all objects used in electronics have a difference between their ideal and real. An ideal battery would have 0 internal resistance. It could produce unlimited amounts of current. We don't have any of those. Now, in addition to this, all of our meters are compromised. We have 2 kinds of meters that we've talked about so far, and I'm going to add a third today. We've talked about meters that can be used to measure resistance. I guess we had 4, because we talked about meters that can be used to measure capacitance. We did that earlier. There are meters that are used to measure current. There's meters that are used to measure voltage. And we've been kind of stuck with just using a couple of them, but we're going to start using more. A meter generally is symbolized as a circle with whatever it's measuring in the middle. So a circle with an A, ammeter. It's not spelled amp meter, A-M-P meter. They drop the P. So an ammeter is an ammeter, A-M-M-E-T-E-R. I guess I just don't like having 3 consonants together. Go overseas, there's lots of chances to have 3 consonants together, but ammeter isn't the thing. Voltmeter, V with the circle around it, simple enough. I'm putting them the way they have to be connected. Voltmeters have to be connected across the source upon which you're trying to measure voltage. They're measuring potential difference between 2 places. So when you're using a voltmeter, and today you used it really for the first time, you're measuring the voltage by placing the common at the low end of the voltage and the positive or the red end at the upper side of the voltage. If you measure a voltage and you find it to be negative, that simply means that you put the common on the high side of the voltage. So voltmeters will just reverse and give you a negative sign. Does that make sense? Do I need to say that again? All right. Amp meters have to be placed in line with the element to which you're trying to measure the current. So you'll notice in this particular circuit, I can add a voltage source over an active circuit, but I have to break a circuit to add an amp meter in. You understand why I'm saying that? Because the voltmeter can just be added in parallel right across the top of a resistor. You can have an active circuit and just grab your voltmeter and measure voltage real quick. You can't do that for an ammeter. And by the way, I've never said this before, but it probably warrants being said. You can't measure, or you can't use the multitesters to measure resistance while a circuit is activated. Okay, so if you select the resistance side and you try to connect it to a resistor, it will not tell you what the resistance is. It will tell you something, but it will not tell you what the resistance is. And that's because of the way the meters work. The meters actually work by almost always measuring current. It's the one thing they can really measure. They can measure voltage a little bit, but usually not inside an active circuit. They almost all measure current. The way they do that is by sampling the current as it passes through. So for a voltmeter to measure current, for a voltmeter to measure potential difference, it actually trickles a little current through itself and measures the current and calculates the voltage. To do that, the voltmeter tries to not interrupt the circuit, but it has to pull a little bit of current. So adding a voltmeter changes the circuit. Voltmeters try to have high internal resistance. A voltmeter tries to have high internal resistance. It may not be obvious why that's true, so let me make it a little obvious. If it has a very high internal resistance, when placed in parallel with something else, it won't change the overall resistance very much. Just a reminder, let's say that it has an internal resistance of 100,000 ohms. It's probably way higher than that. And let's say this is a 2 ohm resistor. What's the equivalent resistance of this system? Well, it's 1 over 2 plus 1 over 100,000 equals 1 over R. I've got my old handy-dandy calculator here. 2 inverse plus 100,000 inverse, add them together, and then invert my response. And I get equivalent resistance of 1.9996 ohms. So does it affect the overall resistance? Yes. Is it measurable? Probably not. Probably not with the meters that we have at hand. But it does affect the circuit. So that's our first thing. Voltmeters have a very high internal resistance. They attempt to measure a small amount of current and use that to calculate voltage. Now, an ideal voltmeter has infinite resistance. An ideal voltmeter would have infinite resistance, meaning it will draw no current and not affect your circuit at all. There are no ideal voltmeters. Now, ammeters try to measure current. They have to be in series. What do you think about their internal resistance? That's right. Very low internal resistance. However, they're going to have some. Because they have some, they will actually reduce the overall current in the circuit. They add resistance to whatever leg they're being added to, and therefore reduce the overall current. When you add an ammeter, what you will measure is less current than is likely in the circuit when it's not there. Now, the only way to do this for most multi-testers is to have separate input connectors. This is why, if you've been paying any reasonable attention to me in class, I've always been saying to you how to connect your meters. This one was no difference. Whoever had this meter probably didn't take very good measurements. This is not pushed in all the way. You guys have to push your terminals in all the way. They should be all the way in. So I don't know who had this meter, but you might have been trying to take the cables out or something, but they need to be all the way in. You'll notice that there's always other connectors here that we haven't been using. We haven't used these to measure current yet. But the input connectors to measure voltage are on the side that has the really high internal resistance on purpose. When you want to measure current, you want to go to something that has a very low internal resistance. It's different circuitry inside the device. You leave the meter in the common and you switch this to one of the other measurement points that measures current. That way the actual internal resistance on this side is very low. So it's separate circuitry and everything in order to measure the current. And that's why you have to change the meters. No matter how nice the meters are, and I've got some that are nicer than others, even multi-scaling electronic meters will have to have separate places to connect your wiring in order to ensure that you're presenting your circuit with either a very high resistance or a very low resistance for the circumstance in which you're measuring it. And the reason why there's 2 extra places here for current is because one of them is fused. Not anymore. Most all the fuses have been blown out because almost everybody tries to measure the current in the one that's too small and pulls too much current and blows out the fuses. I've stopped replacing them. So when we go to measure current, our best bet is to measure over here in the 10 amp side. It's the non-fused side. You pull 10 amps, you'll melt the meter. But it's not fused. You understand? Meters. Now, we'll be using the current side of the meters later, but I still want you to understand internal resistance. All devices have a certain amount of internal resistance. Internal resistance isn't a resistor, but can be treated like one in all circumstances. Current meters have very low internal resistance. Voltmeters have very high internal resistance. Ideal voltmeters, infinite resistance. Ideal amp meters, 0 resistance. That's right. Ideal amp meters will be 0 resistance. All right. Today we're going to start our conversation about RC circuits. Resistor circuits are okay, reducing them, finding the voltage, fine. Capacitor circuits are okay, reducing them, finding the charge, okay. None of that particularly interesting. To me, this is where we start getting into what circuits can do. These are going to be transient circuits, circuits in which something happens over the course of time. The whole point of building a circuit is for it to have some kind of functionality. Now, still, we're not really getting to a point where we're going to have a lot of functionality, but we're going to begin to understand why I think circuits might be interesting. And we start with the RC circuit. Now, to understand what we're going to be doing here, please be very clear. RC circuits are transient circuits. Transient circuits, which means something changes over time. We never noticed this before because we were only dealing with capacitor circuits by themselves and we weren't really using them in any meaningful way. From this point forward, we're going to start using them in meaningful ways, taking measurements. And the first thing I want you to recognize is that in this circuit, there are two obvious and complete states, and then there's the transient part of the circuit. From now on, we're going to start using some terminology. There is the time equals 0 state, and then there's what's called the steady state. The time equals 0 state and the steady state. The time equals 0 state is what the circuit is the exact moment that you close the switch and connect the elements. That's the time equals 0 state. The steady state is known as the state of the circuit after it has been connected for, and this is a very technical term, a very long time. That's the phrasing you have to look for in your homework, look for in your problem. In the middle is the transient state, the time during which the circuit is changing. I want you to look at this circuit in a very simple fashion. Let's assume that at t equals 0, the charge on the capacitor equals 0. This is our initial state of the circuit. In the time equals 0 state, when I close this switch, there has to be an opportunity for charges to move from one side of the capacitor to the other. During that time, those charges have to be pulled from one side of the capacitor, move through the circuit to be deposited on the other side of the capacitor. Which means when I first close the switch, there's likely to be a current detected at the resistor, because charges have to be pulled through the circuit to charge the capacitor. There will not be a current across the capacitor. The capacitor will never pass current until such a time as the capacitor fails. At that point, it's no longer a capacitor, it's just a wire. But as long as it's a capacitor, it never passes current. But the rest of the circuit acts as though there's a current in the circuit. Now, the moment you close the switch, that current becomes active. But after a few moments, charges begin to build up on the capacitor. This prevents the flow of more charges from moving through the circuit. The more charges that are on the capacitor, the less charges that can move through the circuit. So as the capacitor charges, the current in the circuit begins to drop until such time that the capacitor is fully charged. When the capacitor is fully charged and no more charges can fit in the capacitor, we reach a steady state and the current in the circuit must drop to 0. So T, after a long time, reaches a steady state condition in which the capacitor is fully charged and there's no current in the capacitor leg. You'll hear me start using this phrase, one leg of the circuit versus another. It's to indicate the options, the pathways that exist to a circuit. This circuit that we have drawn here only has one leg. So if the current through the capacitor goes to 0, the current through the whole circuit goes to 0. Now what we need to do tomorrow is what I think is the most important thing we do with RC circuits. We're going to apply Kirchhoff's rules to the circuit to get I as a function of t. This is a very important discussion tomorrow, folks, and it's kind of challenging. Please be here for it.